In this video, we'll be giving a bit of an overview of fluid power systems, what they actually are and how they actually work. And these are common types of actuators that are used in robotic systems and industrial sort of settings as well. So with our fluid power systems, we're talking about actuation that uses some sort of pressurized gas or liquid to transmit energy, rather than electricity that we looked at in one of the previous videos. And we've got two fundamental types here. We've got hydraulic systems that use a compressed liquid, like an oil or something like that. And we've got pneumatic, which use a compressed gas, typically air, to perform this sort of task. Now, one thing that these both rely on is Pascal's law. And basically, Pascal's law states that an increase in pressure at any point in a confined fluid, we have an equal increase at every other point in the container. So here's a bit of a diagram that illustrates the power of Pascal's law, particularly when we're trying to lift a heavy weight and gain mechanical advantage over it. If we know that force is equal to pressure times our cross-sectional area, and we know that our pressure between these two cylinders is consistent, then we can actually work out the force that we can apply to lift something in our second cylinder, and also the distance that we're actually lifting that by. So for our first cylinder, we have a cross-sectional area there of 10 millimeters, 1 centimeter, it's quite small, and we're moving at a distance of 100 millimeters. Our force that we're applying to move it is 100 newtons. And so what we can say is the pressure is the same, so P1 is equal to P2. We have the same pressure in each of our cylinders there. And so we can say, since P1 is equal to P2, F1 on A1, so 100 newtons on 10 millimeters, is equal to F2 on A2. F2, which is what we're trying to work out, on A2, which is 50 millimeters. We can then rearrange to find F2, and we find in this case that F2 is 500 newtons. So by applying 100 newtons of force, or if we're talking in mass terms, maybe 10 kilos when we're figuring gravity, we can lift something that is 5 times heavier than that, 500 newtons or 50 kilos. Now we can scale that up to use significantly bigger cross-sectional areas, particularly in our second cylinder, and we can pick up very large weights. And this is the sort of hydraulic sort of mechanism that we use to pick up cars, for example. Likewise, our volume between these will change, because when we change the volume in one cylinder, the volume will change by a corresponding amount in the other one. Now, the volume is equal to our cross-sectional area times the distance that we've actually moved. And so if we say V1 is equal to V2, the cross-sectional area, A1, times the volume that the distance we've moved in the first cylinder, D1, is equal to A2 D2. And we can work out here that for our distance moved of 100 millimeters on the input, we move a distance of 20 millimeters on the output. That's D2 there. We've already seen it, but we're generally using cylinders and pistons in these sort of environments. Cylinders use air pressure or some sort of a liquid to move the piston in a linear motion, used in hydraulics and pneumatics depending on which one that we're working with. And we pump in this fluid or this gas into an inlet, and that pushes the cylinder along. Now there's a whole lot of key terms related to pistons and hydraulics and things that are useful for us to know. Firstly, we have the piston, which is the moving part that's actually moving inside our cylinder back and forth. And we also have the bore. So the bore refers to the internal diameter of the cylinder. Typically, we've got a seal around the piston, an O-ring or something like that, which allows it to fit really tightly inside and slide inside the cylinder. Now, the bore is very important for us to know because it gives us the cross-sectional area that that cylinder will have, and then we can use Pascal's law to work out the force that we can apply. And we have the rod, and this is attached to the piston, and it's the part that actually comes out of our cylinder and everything, and the thing that we actually bolt things to. We also have the stroke, and this talks about the total travel that's available for us, the distance between when it's fully retracted and fully extended. So how much stroke we have in our rod. We have a gland as well, and that's the part that the rod actually moves through. This is basically a gasket there, and prevents contamination of particles and things getting into the cylinder and causing rust or whatever is going to happen in there. Now they can be in a few different forms. They can be single acting, so in this case we only have one inlet. When we apply compressed air or something like that, the piston's moved, and when we don't supply it, a spring will push the piston back into position, so single acting. We can have double acting. This is where we have two inlets. So we can apply gas or liquid in one spot and move it one way, and then we have another inlet where we can apply it and we can move it back in the reverse direction as well. It really just depends on what sort of environment that we're working in, whether we can have a spring action to take it back again. Now, in this case, in the double acting case, when our inlet's not actually driving, it should be connected to the exhaust. And this is where our air can pass out freely and vent out into the environment. So here's a diagram of how it would look. Remember, we've got our force is equal to our pressure times our area of the piston. We apply our fluid or our gas into that first inlet, and everything inside that second inlet is pushed out through our exhaust point. And likewise, when we're moving the other direction, it's pushed out by that other exhaust point. When we're using a hydraulic system, we don't exhaust out into the atmosphere the fluids there. We'll send them around our hydraulic circuit and keep them circulating.